All right, so now we're going to pick up with our second video here. We're going to talk about conservation of momentum. So, conservation of momentum is just like this idea that, momentum kind of has to be conserved, and it relates to Newton's third law. So, if you remember back to the third law, the force on one object was equal to but opposite the force on another. So, if we think for impulses, we can rearrange impulse, J equals F delta T, in terms of forces. So force would equal impulse over change in time. So if we're talking about the impulse on object B over a certain change in time, it would be equal to the negative impulse on object A over that same interval of time. Well, if it's the same interval of time, the intervals of time cancel out. It's like saying the impulse on object B from a collision is equal to the negative impulse on object A, right? So if two cars hit, they have equal but opposite impulses on each other. Okay, that doesn't mean that they have the same forces, just they have the same impulses. Now, why is that? Well, they could have different masses, because we can think of the fact that, well, object B is mass of B times the change in velocity for B. And object A is the mass of A times the change in velocity for A. Because again, in a car collision, they don't necessarily have to be going at the same initial speed. And even after the collision, they don't necessarily both have to stop. They could just collide and then just change speed somewhat. All right? Or even if it's two balls, like a game of billiards. So if I expand that out, I now have this idea of a change in velocity as being velocity final for B minus velocity initial for B. And then if I go to the A side, I do the exact same thing. So velocity for A final minus velocity for A initial. Now I had a negative sign there in front, so I'm going to bring that in and just kind of, again, flip the signs here a little bit. So it's, MA times a VAI minus a VAF instead, kind of down here. Right? All I did is just brought that negative in. So it looks just a little bit different. Well, right now I'm just comparing object A and object B. Well, what if I'd rather talk about, like we did with conservation of energy, initial state and final state? Well, to do that, I have to distribute the masses in. And then, once I've distributed the masses in, I bring everything about the final state to one side, the initial state to the other side. Okay? So I find out, when everything's all said and done, and I say, here's my initial state, here's my final state, that for the two objects, when they collide, they're each going to start out with an initial velocity for A and an initial velocity for B. They're going to end with different final velocities. Final velocity for A, final velocity for B. And they've each got their own masses. Okay? Mass A, mass B. And this equation here is our conservation of momentum equation. So all collisions will conserve momentum. Now there's different kind of special cases of collisions we're going to talk about here that, treat this equation slightly different. So again, conservation of momentum is going to apply to all systems regardless of their size. So in a game of billiards, when those two balls collide, momentum is conserved. The momentum of the balls initially is the momentum of the balls finally. When two cars collide, the momentum is conserved. The momentum before the collision is equal to the momentum right after the collision. Even the universe, when a star explodes, right? When a star goes supernova, that collapse, the reason everything gets thrown so violently outward has to do with momentum change. As all the material comes in at one velocity and it kind of rebounds off of itself, the lighter material on the outside gets thrown off violently. Kind of other interesting thing with this idea is recoil. So recoil is related to kind of momentum conservation for objects that are initially at rest. So like when you fire a gun, the gun and the bullet are both initially at rest, no momentum. You pull the trigger, explosion happens, bullet wants to go in one direction, gun recoils in the opposite direction because they have to have equal but opposite momentums to balance out to be zero. It just happens that the gun has a lot more mass than the bullet does. When firefighters are trying to direct a stream of water, well, that water's coming out at a very high velocity. There's mass at a high velocity, right? Almost like a rocket. Rockets are expelling gases at high velocity. Well, in the opposite direction, there's going to be a counteractive force, that recoil force. So, again, collisions occur when two objects strike one another. So the billiard balls hitting one another, a baseball bat hitting a ball, one car smashing into another car, and we're always conserving our momentum. Okay. The one thing that doesn't always have to be conserved, though, is our kinetic energy. Because if we think about car collisions, you know, some of the metal goes crunchy, crunchy, means some heat has to be generated to do that. Well, it means we could lose some kinetic energy. So we then have to start categorizing our collisions based on what happens to that kinetic energy. Did we keep all our kinetic energy? Did we lose some kinetic energy? You know, that's kind of the difference between our types of collisions. So we really have two main categories. We have the elastic collision and we have the inelastic collision. So in an elastic collision, the final kinetic energy of the system is equal to the initial kinetic energy. So we don't lose any kinetic energy. So we conserve momentum and we conserve kinetic energy. The inelastic collision is one where the final kinetic energy is less than, or if it's an explosion, greater than the initial kinetic energy. Right? So like when I fire a gun, you start with no kinetic energy, you end with some kinetic energy. It's an inelastic collision. Okay? Because the kinetic energy changed in some way, it was lost or gained. So it's inelastic. So for the elastic collisions, we're still definitely going to have this nice happy equation. But we also have to bring into account this equation here. Now, you've got these two equations. We know from math, you have two equations, you could have two unknowns. Well, the problem is life can get very unwieldy if you're trying to purely solve with these two equations. So what happens is we get this nice little shortcut equation, all right? It's right here. And we get that from doing some mathematical derivation. Again, in the slideshow here, I'm not going to bore you with it in the slides of the video here, but if you go on to Moodle, I have posted the full derivation there, just because I'd like you to look through it, try to understand what happened with, you know, really simple algebra rules, but you can just do some expansion, some rearrangement, and simplify down to this equation from these two equations. And this one here is the one that we're going to be using the most, so this will be our friend. So what will end up happening is it's going to be, this is our primary, you know, conservation, and this is our secondary when it's elastic that we're going to be using. Just to save us time, save us energy, you know, make us not go crazy with the math. We'll use this, I call it the shortcut equation. So now, for those inelastic collisions, we're going to have just good old, you know, MAVA initial plus MBVB initial equals MAVA final plus MBVB final, all right? Whereas for elastic, we're going to have that plus that derived shortcut equation, all right? And those are our two types of collisions. Within the inelastic, we will talk about some special cases where the things stick together after the collision. They'll have the same final velocity. Sometimes those are called completely inelastic collisions, but it's still the same equation. Nothing special other than just remembering the two final velocities are the same.